As this investigation unfolds, accompanying maps can help visualize the story. We will examine where major data centers are being built, where populations are growing, where water resources are abundant or strained, and where environmental pressures may be increasing. These maps provide a simple way to understand a complex issue: artificial intelligence, cloud computing, streaming video, financial transactions, social media, and the endless flow of information seem to exist somewhere beyond geography, but they do not. Every search, every image, every calculation, and every AI response ultimately takes place inside a physical building, a data center. And data centers consume resources. They require land, they require electricity, they require cooling, they require water, and increasingly, they require enormous amounts of all four. As the construction of large AI facilities accelerates across the United States, an important question emerges: where should these facilities be located? To answer that question, we examined a series of national maps: population density, population growth, annual rainfall, groundwater recharge potential, average temperature, humidity burden, existing concentrations of data centers. When viewed individually, each map tells a different story. When viewed together, a pattern begins to emerge. Many of the fastest growing regions of the country are also becoming major centers of data center construction. These same regions often face higher cooling burdens, increasing pressure on electrical grids, greater competition for water resources, and lower groundwater recharge capacity. The Texas Triangle, Central Arizona, parts of the Southeast, Northern Virginia. In each region, people and computers increasingly compete for the same finite resources: water, power, land, infrastructure. The issue is not whether data centers can be built in these locations. They clearly can. The issue is whether they should. At the same time, another region repeatedly appears across these maps: the Great Lakes, the Upper Midwest, areas with abundant freshwater resources, lower annual cooling burdens, substantial existing industrial infrastructure, strong groundwater recharge potential, and in many cases, slower rates of population growth. In engineering terms, these regions appear naturally suited to support large-scale digital infrastructure. The maps raise an obvious question: if climate, water, and resource availability matter for agriculture, manufacturing, and urban planning, why would they not matter for data centers? Recent events suggest these questions are becoming increasingly important. In Georgia, residents reported muddy well water and concerns about groundwater impacts following nearby data center construction. Federal officials were asked to investigate the situation in 2026. In Fayette County, Georgia, residents experienced low water pressure during a period when a major data center project consumed approximately 30 million gallons of water amid statewide drought conditions. In Arizona, growing concerns have emerged regarding the expansion of water-intensive infrastructure within regions already confronting long-term groundwater challenges. Across the Mid-Atlantic, utilities and regulators are debating how rapidly growing data center demand may affect future electricity costs and infrastructure expansion. The question is no longer theoretical. The effects are becoming visible. None of these issues are ideological. They are engineering questions. Where does the water come from? Where does the electricity come from? How much cooling is required? How quickly can resources be replenished? Who bears the cost when infrastructure must expand? The cloud is not weightless. Artificial intelligence is not virtual. The digital economy has a geography, and geography still matters.